All right, so the last system that we're going to cover is the environmental systems, and that's a big umbrella for a lot of subsystems that we're going to cover. Now, these are all pretty interesting, but there's a lot, and there's a lot happening. So you're gonna have to keep your head on your swivel as you go through this video, which will likely probably become 2 videos if I had my guess, just because there's so much information to kind of cover under environmental systems. Let's first off define like what is an environmental system. Well, it's not talking about the outside environment; it's talking about the inside environment inside of the aircraft. Now that could mean several different things to include oxygen, and it could include pressurization and everything else. Now it's going to be heat, the whole 9 yards. And then you think about from old aircraft like the Cessna 170 that's in our hangar right now that was made in 1948, all the way up to 777X. How varied those systems get. Now, you as an A&P mechanic need to be confident and proficient enough to be able to go and work on any one of those systems. So it's a lot to manage. But what you'll find is that the principles are the same no matter where you go and what you work on. And you just got to get really confident in those underlying principles and then just apply them as you are called upon. So, to get us started, let's start talking about pressurization systems. Now, pressurization systems are really, really important, and we're going to get into why. You don't want your passengers getting hypoxic because you screwed something up on the pressurization system. There's been aircraft that have killed entire flight crews and almost got shot down because the flight crews died due to a pressurization system malfunction, and they just kept on flying, and they wouldn't respond, and they thought that maybe it's like another terrorist attack, and they dispatched F-16s out there to them and say, like, hey, like, what's going on? And you get up close to them, you realize that they're all dead on the inside. This is also a leading theory for MH370. Like, that's what happened to that Malaysian airliner. That there was a pressurization malfunction, and everybody slowly got hypoxic, and nobody was able to cognitively know what to do or how to respond to that situation. And so they just flew off into the Indian Ocean and died. So let's talk about pressurization. Okay, so let's just cover some basic knowledge about the atmosphere and how everything works. Essentially, the higher up you go, the lower the air pressure gets. And the simple fact is that there is less atmosphere above you. So at sea level on a standard day, you're getting 4.7 pounds per square inch. So it means that on every square inch of your skin, you're feeling almost 15 pounds of pressure bearing down on you from just the air above you alone. So imagine like all those air molecules stacked end to end, going all the way up until the atmosphere ends, near outer space, and that'll total up to being about 15 pounds. It's a lot of air, all right. Now, because of that that dynamic, whenever we fly at say like 50,000 feet, we run into a lot of challenges in terms of air pressure. Now, one of them is oxygen, and we're going to get to oxygen here in just a minute when we start talking about oxygen systems. But like the other one is air pressure. It doesn't feel right to be flying around with 2 or 3 pounds of pressure on your body. Matter of fact, one of the big concerns in like outer space is that like if you depressurize that capsule that the astronauts are in, what will end up happening is their bodies will basically pop like a grape or something, or like a balloon. And the reason being is that there's no pressure keeping them in. So you think about you have your blood pressure, your body is built to run around at sea level at 15 pounds a square inch on your body, right, or 14.7 if you want to be exact. And then whenever you remove that air pressure, all the counterbalancing pressure that pushes out on that 14.7 pounds per square inch, there's nothing to push back against it. So all of a sudden you overstrain like your skin, your eyeballs. You'll see like in the movies they always depict them as like they end up having a big nosebleed and their eyes turn red. Well, that's because like their body is just overpressured and they just explode. And so we probably were not going to be able to fly high enough to cause that. But what will happen is a whole host of other physiological problems. So you think about putting your grandma on an airliner as she flies around. You don't want her to be uncomfortable. And so we have to come up with some way to pressurize the air inside of the cabin to maintain the oxygen level for one, but also maintain a comfortable pressure. We can lower the pressure a little bit because people live at different altitudes, and the altitude at the top of Mount Everest and the altitude in Death Valley are two different altitudes and two different air pressures, and so there's definitely a range of tolerance for the human body, but it can't be basically next to nothing, because that's what will cause all of our problems. So, in order to do that, we have developed pressurized cabins in aircraft, and this is how they work. Okay, so first off, let's define three terms that it'll facilitate our conversation about cabin pressure. First off is when they say cabin altitude. That's the given air pressure inside the cabin, the altitude on a standard day that has been the same pressure as inside that cabin. So rather than saying the pressure inside the cabin is 10.92, it can be said that the cabin altitude is at 8,000 feet. So it's a fancy way to say essentially what you're doing is you're simulating living and working at a certain altitude. So you say like Denver's about a mile high, so that's about 5,200 feet, give or take, depending on where you're at. So if you wanted to simulate Denver inside of the cabin in terms of like air pressure, you would set the cabin altitude to 5,200. Even if the airplane is at 45,000 feet, the cabin pressure or the cabin altitude is going to be 5,200 feet, and it'll feel like you're living at 5,200 feet right there. Now, there are limits to like how high you can go with it, and we're going to get into that with oxygen here in just a minute. But basically, anything below like 10,000 feet is perfectly fine. And actually, you can go a little bit higher than that if you wanted to. But just kind of as a rule of thumb, 10,000 feet and under, you're fine. All right, so this graphic that we're looking at here is cabin differential pressure. All right, now that's the difference between the air pressure inside of the cabin and the air pressure outside of the cabin. So cabin pressure in psi is compared to ambient pressure in psi, and that will give us the cabin differential pressure. So let's go back to our Denver example. It's 5,200 feet on the inside of the cabin. It's 45,000 feet on the outside of the cabin. So the differential pressure would be a pressure difference of 40,000 feet whenever you convert that over to whatever the psi would be, or your millibars, or whatever your system is. All right, so the cabin rate of climb is the last one. So you get like cabin altitude, differential pressure, and then now rate of climb. So the cabin rate of climb is the rate of change of air pressure inside of the cabin expressed in feet per minute of cabin altitude change. Now this is what makes people uncomfortable. If most people can stand pressures going all the way up to like say 10,000 feet, and it's fine. What will get people's ears popping and get people like uncomfortable and woozy and all other good stuff is the rate of change in which you get to that 10,000 feet. So if you go like 100 feet a minute, that's really, really, really slow, and like no one will basically ever feel the difference. But if you go from 10,000 feet a minute, so in 1 minute it goes from being one pressure to something totally different, that's when you're gonna get a bunch of people like popping their ears and be all complaining to the stewardesses and all their good stuff. So it's real important to maintain like a good steady rate, probably under 500 feet a minute, because it's kind of like your standard rate to keep people comfortable. So that's the basic vocabulary when it comes to pressurization. So you have like differential pressure, rate of climb, and then cabin altitude. Okay, so now that we know our terms, we can start talking about like how the system actually works. All right, this is the aft pressure bulkhead on a 737. So what you're looking at here is that if you were to stand up in the tail with the APU and the tail flight controls behind you, so you can see the rudder cable goes right down in front of you, right there. You'd be looking forward towards the cockpit and all the seats and everything else, and you'd have this big structure right in front of you. All right, this is the aft pressure bulkhead, and what it's built to do is to maintain the cabin altitude exactly the way that you set the pressure at. All right. Now, effectively, what you have here is a like a super balloon. It's not really meant to maintain pressure from squeezing the aircraft from the outside. It's made to maintain the pressure from wanting to escape, to blow out, so that way you can maintain a higher pressure inside of the cabin than out of it. Now, There is a forward pressure bulkhead as well, but it doesn't look as nearly as iconic as the 737's aft pressure bulkhead. And you see how it's domed over. When you see one in real life the first time, it's really kind of I don't want to say breathtaking, but it's cool because of how you see how big it is, and you see how much engineering and work went into designing that thing to be able to hold that amount of pressure at that altitude. So you can think this thing you could put the airplane on the ground in terms of cabin altitude, and then fly it all the way up to the service ceiling at like say like 40 some odd thousand feet, and it'll hold it, and it'll be just fine. It'll be like super duper high pressure on the inside and super low pressure on the outside. But these airplanes have to be designed to be able to take care of that. Now, what does this mean for you, the technician? You have to be very, very conscious that anytime that you're working on the aircraft exterior, that you could potentially jeopardize this. All right. Now, you'll see in the movies that these planes will like blow out, and they like blow out an entire section of the aircraft or whatever. There's a grain of truth to that, but when you start looking at the engineering of the way that the structure is built, it's actually made to give away in small sections, and then stop the effective like the tearing of the fuselage at different joints, and so the likelihood of you doing something that causes like a massive decompression or explosive decompression like that is fairly low. However, what you could do is cause a section of the airplane to depart, or cause a leak, and you'll end up having to abort the flight. And if you do it in a very sneaky way on accident, you could end up causing people to get hypoxic, and then that will cause people to die. But it won't just be this fantastic explosion or whatever. Now that being said, there have been aircraft that in the past have had explosive decompressions because of different issues along the way, but they're very rare. So like just know that whenever you're working on the pressure bulkhead, you're working on the exterior of the aircraft, like windows, installing antennas or anything like that. This is something that you need to take into account and have the proper engineering approved data to work off of, because this is like no joke. Could be a bad deal if you get it wrong. Okay, so this is a Aloha Air 243. Now, I believe we've talked about this before, but effectively what happened is that you see right beside the crew door there, just going aft the plane, that's where the separation of the fuselage happened. There was actually a row of rivets that gave way. Now, their corrosion was a major factor in all this. That the corrosion inside of those rivets had eventually weakened it and weakened it and weakened it. But what happened was whenever the aircraft got to a certain altitude, the cabin pressure, the differential pressure, blew that front part of the fuselage up. It didn't blow it off. It just caused the rivets to pop, and it popped up. When it popped up, it caught the air, and the air pressure ripped that section of the aircraft off. And you notice that it folded back right there, right in front of the wings. And kind of an aside, this is also the reason why you always wear your seatbelt whenever you're flying on an airliner. Notice how many people are just sitting there. That the reason why they were sitting there and they were able to survive is because they were wearing their seatbelts. There's only one person that died in this incident. It was the flight attendant, and the only reason why she died is because she was up working the cabin, and so she got sucked out whenever all that air pressure washed over her. It's a tragic thing, but this kind of goes to show you the level of pressure that is actually inside of those aircraft. Now, also, the reason I put this up here is that the FAA actually has an aging aircraft program that looks for problems like this before they happen. They study aircraft that have been gone through what they call multiple cycles, so like pressurization, depressurization, pressurization, depressurization. That's a cycle. Anytime you cycle metal like that, you get metal fatigue. So whenever you get to work, and you come up with an NDI inspection, so you're gonna eddy current this section of the fuselage, or these pieces. That's why, like, you're looking for problems before they turn into an Aloha Air 243, and cause massive decompression. So just know that is a factor, is that you need to be conscious of the fatigue the aircraft is undergoing as it flies. The older the aircraft get, the more cycles it has, the more the possibility you have of something like this happening. Things aren't going to last forever. Eventually, they have to be maintained, replaced, and so on and so forth. And especially when it comes to pressurization. All right, and so just so we're all on the same page, aircraft of any size can be pressurized. This is a Cessna Centurion. They call it a P210. So it's a regular Centurion is a C210. This is a P210 because it's a pressurized aircraft. Now these are actually fairly popular in the I have enough money to have a fancy airplane, but I don't have enough money for a jet crowd. These are really common. There's several of them actually on the field in Texarkana. Matter of fact, I just worked on one of them. It's super nice 206, but it could be pressurized. And so you'll see Cessna 182s, 206s, 210s, all that have this feature, as well as a whole host of other small general aviation aircraft. So don't think that pressurization is just for jets or just for large aircraft. They can be small aircraft as well, and frequently are. And you have to be the same kind of rules apply. Is that like that fuselage is made to take a certain amount of pressure, and anytime that you're working, installing different STCs or whatever on that aircraft, you have to be very conscious of what that could potentially do to the pressurization features of the aircraft, because it's going to have a differential pressure limit just like a 737. It's probably not nearly as much, but you could effectively pressurize this thing like it's on the ground, put the cabin altitude at zero, and then take it all the way up to 26,000 feet or whatever their service ceiling is, and it could potentially have a explosive decompression event. So you be really careful about working on the exteriors of these aircraft. Okay, so what are the sources of pressurized air? So let's start off with our our reciprocating engines. All right, so there are three basic ways to pressurize a recip aircraft, and that's through a supercharger, a turbocharger, or an engine-driven compressor. Like I've said, that 206 that we just had in the other day, it actually has a turbocharger on there, and it works just like this. So essentially, the engine, as it turns the turbocharger to bring in that air and compress it and push it into the cylinders, which we're going to get to when we get to power plant. One of the kind of offshoot ancillary things that it can do is take that same pressurized air and then force it into the cabin, and that will turn around and supply pressurized air. Now, the same thing happens with the compressor, just like on an air conditioning unit, which we'll get to here in a minute. You have a compressor that compresses the outside air and then introduces it into a space, this time the cabin. Or you can have a supercharger that does exactly what the turbocharger does, is just arranged a little bit differently. Any one of those three could supply pressurized air to an aircraft, a reciprocating aircraft. Now, whenever you go and inspect those turbos and those superchargers, those air compressors, they're all going to have their own inspection criteria that makes doing the annual on the plane a little bit longer and a little bit more involved, and it is frequently a source of airworthiness directives. So that's something you're going to want to pay attention to. But they all have to be lubricated and taken care of in their own time, and you have to be very conscious of inspecting them specifically for exhaust leaks, because they're just known to have them. But this could be potentially one source, or a way to pressurize a cabin if you have a reciprocating engine. Okay, so there's two basic ways that a turbine engine pressurizes air. First off, is that just simply by using bleed air, and that will do is that like you'll pull that bleed air off, but it's really hot because it's coming right off the engine, and so they have to mix it with some sort of outside air to lower the temperature. They will then put that through a jet pump, and then that jet pump then pressurizes the aircraft, and then that air will go through the outflow valve, and all is happy in the world of the turboprop aircraft. So this is like pretty common with your King Airs, your Pilatuses, and those kinds of things. So that's one way that turbines do it. Now, keep in mind that like the turbine aircraft, they're all going to be similar in about 80%, 80 to 90% ways, and then like they're very unique in the last 10%. So you always have to kind of go to the manual and read the general description of how a system works before you really start wrenching on it, because there might be little nuances to a turbine aircraft that can make a big difference if you don't pay attention to it. Okay, so probably the more effective way to do it, because the problem with doing it the way that we just talked about is that you can only pressurize a small area. So small aircraft will have that, and they have less moving parts and they're simpler, so that's good. But for the majority of your larger turboprop aircraft, you're going to have a compressor to be able to effectively pressurize the space of the cabin. And so what this graphic shows is how that kind of works. You take the bleed air and it actually spins the compressor. The compressor then just grabs outside air, pressurizes it, and then puts it into the aircraft. It's a far more effective way of pressurizing the aircraft. But you have to deal with the compressor now. You have instead of having just the bleed air, basically pressurizing the outside air and pushing it into the fuselage. Now you have another thing that could go wrong. One thing to run up maintenance costs, and one thing you have to inspect. Now, for a lot of these guys that operate this type of aircraft, the extra maintenance cost is not really that big of a deal, and they don't even mind paying kind of a premium to minimize downtime, to throw a lot of guys on this one aircraft to get it back up, because their main thing is that they want to keep the aircraft flying, so that way they can use it as much as they possibly. And if you had a multi-million-dollar private aircraft, that's totally understandable why you would want that. But so it's kind of the trade-off with the turbine approach to pressurization is that, one, you could have it like cheap and simple, but if you do that, you're not going to be able to pressurize it as well or as big of an area. You're not going to be able to fly as many people or as far or as high and all that good stuff. Or you can have a compressor on there and you ramp up the cost of the system, but you're able to do a whole lot more with it, which is kind of like a dynamic that just that surrounds business aviation, is that like you're always kind of having to do a spreadsheet analysis of like, well, how far am I flying, how many people am I flying, and like what's my budget, and then that kind of like will put you in a category of what aircraft you actually need, and these are some of the things that change that aircraft based on the way it operates and the way it ramps up the cost. Now your jets, your Hawker, your Challenger, so on and so forth, all the way up to your Boeing's and Airbus aircraft. They're going to use their air cycle system or vapor cycle system to pressurize that aircraft. They're not going to have a outside air compressor or anything else to just pressurize just the cabin, because they also have an environmental system to control the temperature and all other good stuff. So we're going to get to that here in just a minute, but that's how you do jet aircraft. All right, so now that we understand what pressurization systems are and like how they work, let's talk about the individual components and the inspections that come with those on a regular routine maintenance. Okay, so this is an example of a pressurization control system on a small transport or business jet. Notice that it utilizes a combination of electric, and pneumatic control elements. So we'll just start with the top left, and we'll just work our way around. All right. So first off, you have a regulator, a manual regulator that you can change things manually if need be. And this is all inside of the cabin. Notice that there's a delineation right above that manual regulator between atmosphere and cabin. So this is happening inside, but there are also components kind of on the outside that we need to pay attention to. All right. Then we have to feed the information in somewhere about what's going on outside of the cabin. So you have a static pressure source that comes in there. Usually this is going to be independent of the pedostatic system, but I don't see why you wouldn't be able to also pipe in the static pressure from from the pedostatic system. Now, every aircraft's going to be arranged a little bit differently. It's just going to take that for what it is. Then you're going to have a air regulator and a regulating valve that is going to go to the pump vacuum source. All right, so it's basically going to say like, hey, look, this is the pressure that we want it at. These are the limits. We don't want to over pressurize the cabin or even under pressurize the cabin. We want to make sure that it's within limits, whatever those limits are for our individual aircraft. All right. So kind of going down, so we're just keep on going clockwise. We have our secondary outflow valve that now the outflow valve is basically where the air pressure is going to come into the aircraft. It can't just stay there, right? Because if you did, you imagine just blowing up a balloon. Eventually, it's going to pop. Something's got to give way, and it's going to be very, very uncomfortable to be inside of that aircraft right, before it does. So it has to have a way to right, and the way it does that is through a outflow valve. Outflow valve. So effectively, the valve opens, lets air out, or can close to help bring the pressure back up. Effectively you're kind of turning on and off. Imagine like kind of like a bathtub, right? So the bathtub is like your cabin pressure. And what you want to do is like you want to close the outflow valve, or you want to plug the bathtub up and turn the faucet on and let the water build up. But at some point, if we get too high, the water's going to spill over. So what we want to do is pull the plug so that way as new water comes into the bathtub, old water goes out of the bathtub, and we maintain a certain rate. Now, if we need it to the water to come up, then we might like you want to close the plug a little bit, maybe cover up only half of the hole, or whatever, because then we'll get a certain rate of water climbing in the bathtub, or maybe we adjust the pressure or the water that's coming into the bathtub. Now, if you think about it like that, this is pretty simple. The air pressure is going to come into the aircraft through bleed air or your compressed air or whatever the means is for this aircraft, and then it's going to exit at the outflow valve. And so those two outflow valves right there are pretty key to maintaining that pressure. And if you'll notice that both the secondary outflow valve and the primary outflow valve are tied in both to the static pressure that's coming off of the manual regulator, but also electronically to the cabin pressure sense port. Now, what that's going to do is going to say like, hey, look, I'm looking at the outside air, and I know this is what the outside air is, and then I'm getting data in saying like, hey, this is what the inside air is from our different outflow valves because they're also tied into it as well. And then we're also going to look at what the cabin pressure selector is. What does the crew want the pressure at? And then that pressure sense port is going to more or less open and close those valves to try to keep the pressure where it wants to be. And that's basically the kind of the gist of the system. A lot of the other stuff that's on this graphic are just like the relays and things that like the emergency depress switch and your mode switch and your takeoff and throttle switches. So during certain situations, you want the plane in a certain configuration for safety reasons or maybe even efficiency reasons, and so those relays are kind of essential to it. But it's more or less noise for us at this point. We just really want to focus on a couple of things, like one that pressure controller, their cabin pressure sense port is what they're calling it here, the pressure selector, the outflow flow valves, and then where the pressure is coming from. Those are the key components of a cabin pressure system. Okay, so this is an example of what a pressure controller could potentially look like. Notice that you have a rate selector. That rate selector is going to tell you like how fast the cabin pressure is going to change, both up or down. And what that's effectively doing is it's controlling the outflow valve, either opening it so big or so small. Based on also the outflow valve is going to be looking to see what the pressure is coming in off the engine, because as the engine cycles up or down in different phases of flight, you're going to get different air pressure coming in depending on the type of pump and compressor that's installed on the engine. So there's a lot of variables here, but the so what of it is the pressure controller is the device that's going to more or less dictate what that pressure is. You can also say that it indicates maximum altitude before the differential operation. So it's looking at both the altitude inside and outside and the differential pressure. You're going to have a barometric pressure correction knob. So remember that barometric pressure it's not a static linear thing that like at sea level it's always 29.92, and then at a mile high it's this, and so on and so forth. You're always going to set the pressure of the airplane to whatever it is on the field, because when you land, what you don't want to do is open the door and blow grandma's wig off, either out of the plane or into the plane. And so what you want to do is you want to match the aircraft pressure with the landing field pressure, so that way whenever you open that door, door, it opens easy, and there shouldn't be any air going one way or the other. It should be exactly equalized, so that way everybody's comfortable and no drama occurs. And that's what a successful door opening looks like. Anyways, you have a cabin altitude selector knob that's going to allow you to do that. So you're going to adjust the barometric pressure, whatever it is, on the field that you're landing at, and then you're going to adjust the cabin pressure to mirror that, so that way you get a nice good door opening for grandma. You don't want to knock her down or anything like that. Okay, so this is a kind of a graphic that shows you what a pressure controller might look like on a 737-800. Notice you have cabin altitude on kind of like your top left there, the big dial, and then you have a cabin climb, up or down. It's telling you what the rate of change is. Now you have a flight altitude that you're going to put it at. So if they know that their cruise altitude is, they're going to try to make sure that's in there, so that way the controller knows exactly where they should be. And then they have a landing altitude. So that's where you're going to set the landing altitude to say, hey, look, we're going to land at 800 feet or whatever. And so it should correct that interior pressure to match the pressure on the outside of the aircraft. Now you have a manual opener close option for the valve, and then a automatic or manual selector on the bottom right hand side. Now most of them are all automatic. All you do is just input the variables during pre-flight, and then whenever you land, it's going to do it all for yourself. However, as a maintainer, this actually may be useful for you. I'll tell you a story on a Virgin America flight we ended up getting whenever I worked at an MRO. 2 or 3 rats had gotten in there and chewed up the wires pretty bad, and the problem is that you could work on the airplane and get it back to set up, and the rats were still on board the plane, and no one could catch them, and we couldn't catch them in traps or anything else like that. So one guy had the idea of basically setting the plane up so that way it was at an extremely high altitude, and it basically depleted the oxygen out of the thing. We let it set for a pretty good while, and more or less it caused the rats to die, and then we started going through the blankets trying to find the dead rat bodies, which you never really knew how many were there. I think we ended up finding 3 before I got moved off that project onto another one, so I never found out what the end conclusion was. But this is like a way you could end up using this. But if you're going to you'll end up having to do what's called like high blow or low blow. You probably won't ever do high blow unless you work at Boeing, because it's really dangerous. But low blows, like you'll end up having to do, you have to test the pressurization system on board the aircraft to make sure that it's working correctly based on any kind of maintenance that you'll do. So you have to get familiar with this panel. But really, it's pretty easy to operate, and then the AMM is going to walk you through it, like Barney style. So you don't really have to worry too much about it. Just know that that's kind of a thing that you might end up having to do. Okay, and this is what the outflow valve actually looks like. You've probably seen them before if you're the type of person, and if you're in this class, I would imagine that you are, that kind of pays attention whenever you're at the airport and you're kind of like looking and wondering what everything is. This is what the outflow valve is. It's actually not small. It's fairly large. That door opens and closes to get the help adjust the pressure and let the air that's inside the cabin open. And this is a breakdown of what that pressure regulator and outflow valve actually looks like. So you'll notice that you have inputs for the true static atmosphere connection that comes in there. You have a differential control system, an isobaric control system, and then a filter that filters in that cabin air that helps allow it to compare, and then make mechanical decisions based on what that comparison looks like. You have your cabin air inlet, a ground test valve, and then a dump solenoid. If something gets clogged up, you can open up that dump solenoid, and it'll dump that air for you. And then atmospheric vent ports on the side of it. But essentially, this is what's behind the little flapper valve on the aircraft. And you may end up. I will tell you, these things do they do get messed up from time to time, and you end up having to replace them. And then what you'll do is you'll just replace the valve body and reconnect everything, and then you'll do a low blow test, and it's not really that big of a deal to have to work on them. But this is kind of like the meat and potatoes. Like, granted, like your bleed air and all that good stuff is what pressurizes the aircraft actually, but the outflow valve really is kind of the center of gravity for that entire system. So whenever the bleed air or your pressurized air comes into the cabin, it doesn't just go into like one vent that just blows down the fuselage or anything. It goes into a whole matrix of duct systems that then get dumped into the airframe. Now you're probably pretty familiar with this if you think about getting on an airplane and then you sit down, you look up and there's like air blowing down from one of those little vents that you can screw on or screw off. That's an example of one of the duct systems that are there. But there are several other ones that come up primarily on the overhead duct that you may or may not be aware of, depending on the aircraft that you're getting on. But they'll that air will come in from the engines or wherever that it's generating from, come into the bottom of the fuselage and go up the side of the fuselage behind the interior panels, and then up into the roof or up into the overhead bin space, and then kind of come out that way. And that is a way to have it. Now, granted, the ducting and the routing of all this is unique to whatever aircraft in question at the time, but that's generally the way that it will work. And this graphic here does a pretty good idea, giving you an idea of how you could pipe air into the cabin. But the main takeaway is that there is a ductwork system, and it doesn't just like blow air straight down the cabin or anything crazy like that. Okay, and this is what the actual pressurization system looks like on the 737 MAX. Notice that you have a pressurization control panel. It's very similar to the one that we looked at with your manual control of the outflow valve on the top right, and then you have a selector there. You can put it on auto manual. You put your landing altitude in, and then your cruise altitude. And there's a series of cautions and warnings that can be illuminated. And this is all on the P5 panel overhead. So you're sitting in the pilot or co-pilot seat, you look up, and it's one of the little boxes that is mounted to the P5 just ahead. Now, you're in the eBay, there's a digital cabin pressure controller, just like a little box, and you can bite check that box on the front there. So if you end up having a pressurization problem, that's probably your most likely culprit, especially if it's a newer airplane. If it's an older airplane, there could be any number of things. And then your outflow valve is there as well in the very, very back. And you can change those out as needed based on whatever your troubleshooting that you arrive at. But you notice it's not really that complicated. It's a pretty simple system, and it's just basically there to manage air pressure inside of the cabin, and that's it. We'll talk about bleed air here in a little bit and how the 737 MAX gets pressurized itself, but that's how you manage the pressure once it has been introduced into the airframe. Pressurization is fine and dandy, but if you don't have air to breathe to be able to stay alive up north of 12, 13, 14,000 up to 45,000 feet, then it's all for naught. So let's talk about oxygen systems and the different types that are available out there and that you'll probably encounter. All right, before we get too far into the system, let's just try to understand why we need the oxygen in the first place. Now, this is kind of a layout of what our atmosphere is actually made up of, what we commonly call air. Notice that the vast majority of it is actually nitrogen, which we don't breathe. We breathe oxygen, and it sits at sea level at a kind of an ideal oxygen level is about 21%, and then you have some trace gases that are in there as well. And then if you look at that as humans need 21% air at sea level to be able to respirate effectively. Now, the higher up you go, the less air there is, so in proportion, the less oxygen there is. So you'll get to a certain level where there simply just isn't enough oxygen to sustain life, and that's what we call a hypoxic state. And whenever someone starts to not have enough air to be able to continue to operate, they are hypoxic. Now, hypoxia can very well be deadly, and there's actually 5 different types of hypoxia that you'll have to memorize if you go get your private pilot's license, and it all comes from the different ways that you can get hypoxic, because ultimately hypoxia is just like the lack of oxygen in the blood. So, like say if you had some sort of substance in your bloodstream, there's not enough room for the oxygen to be in there, so you can actually be more susceptible to hypoxia that way. That's just an example. But we don't need to know that for our purposes. We just need to understand the symptoms and consequences of hypoxia. So we have here on this graphic, headaches, seizures, shortness of breath, neurological symptoms like disorientation, confusion, altered mental state, depression, and sluggishness and tiredness. One of the ways that you, as a pilot flying along, can know that you're hypoxic is that, like, if all of a sudden you start getting a headache, or it's harder to breathe, or any of those numbers, and your altitude is always going to be one of the canaries in the coal mine too. You're generally not going to get hypoxic unless you're going, high up. Now, the way the military trains this part of aeromed is that they actually will induce hypoxia into their aviators. And so at different oxygen saturation levels, they'll have these pilots actually do different things on those little switchboards that are in front of them. Now, back in the day, they used to like get them to play cards and do different things. And they'll start to notice, like, hey, look, it's hard to getting to do these tasks they're telling me to do, and what that does is it breeds a certain level of familiarity with hypoxia. So that way, if it starts to happen, they know that it's happening, and that they know to take the corrective measures before it gets bad. Now, we as maintainers, we don't necessarily have to worry so much about all of these effects on us, but we are responsible for the systems that prevent this from happening to somebody else. Those are the oxygen systems. Now, one of the things that you're going to do throughout your career as a maintainer, especially if you're working on jet aircraft or any aircraft that has a supplemental oxygen system, which can even be small piston aircraft, is servicing the oxygen system or maintaining it. What you're going to use for there is typically it's going to be what's called aviators breathing air. Well, effectively, what it is just liquefied atmosphere, and it's been treated so that way there's no oxygen in it, or no water vapor in it to prevent it from freezing up in any kind of small ports or anything like that. But this is what you're going to effectively install, and it could be like a small tank that just attaches to somebody's face and has a little canister just to get them kind of back down to an altitude where they can breathe again. It could be a canister inside of the airplane, maybe like behind the pilot seat that just goes to this little canicle that goes in their nose. It could be inside of the walls, or it could be like in the Lear, it's in the tail. We have a big oxygen tank that's up there just for the crew, so that way they can have supplemental oxygen if they need it. Another oxygen delivery system is liquid oxygen, or LOX. Now, you generally will only see this on military applications in space. And the reason being is that it takes a lot to compress the oxygen down into the form of LOX, and then be able to handle it safely afterwards, because it's extremely explosive. But it can be used for a lot, and it can also supply a enormous amount of breathing oxygen whenever it's decompressed into a system. But it's extremely expensive, and like I said, difficult to handle. So typically, aviators breathing air is what you're going to find on most parts of the civilian aviation sector. But you could run into LOX, especially with the budding space industry that's coming about. You're probably more and more likely to see this as opposed to breathing air or something like that. Okay, another one that is a very common oxygen system are oxygen candles. Now, you can find these in a couple of different places. Like, for one, they may be somewhere on board the aircraft in case of a O2 system failure. You could light one of these candles off, and it'll supply enough oxygen. So, sodium chlorate is what makes up the candle, and then when it burns, it actually produces oxygen. So you'll hear a lot of people talk about like oxygen candles, but effectively what it really is more like, if you're familiar with like the old military style smoke grenades, that's basically what you've got here. Like, you pop the candle, and it's going to get really, really hot, so you definitely don't want to hold it in your hand or anything like that, or put it in a place that it's going to be sensitive to heat. Put it somewhere it can you can get hot and not char or anything else like that. And it's going to produce oxygen for about 10 to 20 minutes, depending on the situation and the individual candle in question. So you've got about 10 or 20 minutes to get to below, say, 12,000 feet to where you can actually breathe the air again. Now, another place that a device similar to this will happen will be in the overhead compartments inside your heavy commercial aircraft. The oxygen masks that drop down are actually usually tied to a system something like this. They won't necessarily be in like kind of the hand or the smoke grenade fashion. They may be in just an oxygen generator. Kind of packet that's up there, but effectively it's the same thing. It's going to chemically light it off, and then it's going to burn for about 20 minutes, about 15 minutes worth of O2. Now, the thing with these is that once you get it started, there's no going back. It's gonna go, and it's gonna burn the whole thing out. So just know that if you ever set one off, you're replacing it. Okay, another kind of neat system that is it's out there. It's definitely in the military side, but it hasn't really wandered over to the civilian side yet. But it's anticipated that'll come is OBIGs, or the onboard oxygen generation system. So without getting into the chemistry of it, effectively you can take oxygen out of the atmosphere, hyperconcentrate, and put it back into the atmosphere, and that's effectively what this does. Now. OBIGs I worked around it, never really worked with the system or on the system on the KC-46 and the P-8, and it's pretty cool. So you don't necessarily need like canned oxygen or a candle or anything else like that. It can generate its own oxygen on board through a chemical process. And this is definitely the way of the future, but it's not out there just yet. So no, you'll see OBIGs probably getting employed at some point. But it's the only people that have it right now is the military. Okay, let's talk about the just kind of the anatomy of your oxygen storage cylinders. So you have a cylinder itself that's usually made out of either steel or aluminum, but they could also be composite, which is good because it actually reduces the weight and decreases the chance of corrosion. Now, if you have a cylinder that gets below 50 psi, you want to immediately take it out of service and get it serviced. And the reason being is that anything below 50 psi, water vapor can actually condense and form on the walls of inside of the cylinder. If that happens and you're using especially a steel cylinder, you could turn around and get corrosion in there, and then you create a weak point in that cylinder, and then you're susceptible to all kinds of problems. So imagine you have a corrosion point inside of the inside wall of the cylinder that you can't detect, but then you put it on an airplane. It flies up to high altitude. It's under a high level of pressure. You can have an explosion in that tank. So it's really crucial that these tanks are maintained properly, because you can't really see the inside unless you do a lot of test work afterwards. So it's just better to just make sure that they are maintained at or above 50 psi. Now on top of it is going to sit a regulator. That regulator is basically like a valve that's going to let a certain amount of oxygen come or out of the tank as needed. Now this is a sample of a continuous flow system that you're looking at right now. It's its simplest form. All it does is it allows oxygen to exit the storage tank, and then through the valve, and then through a regulator or reducer attached to the top of the tank. That's what that little silver guy is on top of the tank there. Now the flow of high pressure oxygen passes through the section of the regulator that reduces the pressure of the oxygen, which is then fed into a hose and attached to the mask as worn by the user. So effectively, the tank leaves the oxygen leaves the tank, goes through a hose, and goes into your lungs. And it's got a continuous flow system, and it's fairly simple and straightforward. And you'll see this a lot on small aircraft, especially small unpressurized aircraft, or in emergency systems, because there's not a lot to mess up. It's just oxygen in a tank and a hose to a mask. All right, this is what it could potentially look like on board a small aircraft that has a continuous flow system. Notice the thing that I want you to pay the most attention to is the charging valve. Because because that's what you're going to end up doing. You're going to end up like hooking up and servicing the oxygen system on a regular basis. This could be on a regular basis that says like every week or so you're going to go check the oxygen level or whatever, or after so many flight hours, or simply just during pre-flight the pilot knows, hey, look, our oxygen is getting a little low. We need to get it serviced. Not a big deal. Take the oxygen tank out there, hook it up there, and then charge it, raise the level up there, close the valve, and off you go. No big deal. But that's what that charging connection is going to be for. Now, there's a filter on there to make sure that whatever you might have accidentally induced will get caught by the O2 filter there. There's a check valve to make sure that the whatever's inside of the oxygen system stays inside the oxygen system, doesn't come back out. And then there's a shut-off valve to the cylinder. That shut-off valve is there so that way you can change the cylinders out as needed, because they have a life limit on themselves. Most of your tanks are only good for like 5 years, and then you have to swap them out. And usually there's a little core charge on them, and you once you have one, it's really not that bad to swap them out. No big deal. There's another filter, same reason, just more redundancy. And then there's a pressure gauge that's what you're going to go off of whenever you're servicing it, and what the pilot's usually going to pre-flight. There's going to be a pressure reducer, and then a pressure regulator, and then the green blowout disc is another thing that I want you to pay attention to, because that blowout disc for the oxygen is something that you're going to see on a regular basis. And so if you see that disc that is exploded, somehow compromised, then you know that the oxygen system has been overpressurized, or there's been something that has gone wrong with it. You'll know that you need to service it. From there, you go up to the calibrated orifices, and then the mask outlets. And the mask generally will plug into that. Now, we actually don't have masks for the Lear, but like typically, you'll have these aviator masks that look like kind of like a. It always reminds me of like the face huggers from Alien, that they go onto your face, and you have these rubberized headbands that go around the backside that hold it really tight up against your face to allow you to get the most oxygen as possible, because it doesn't do a whole lot of good. And as a matter of fact, it can be super dangerous if there was a mask leak because the oxygen was blowing by on your cheeks or whatever. You would think that you're flying okay and you're okay and you're getting oxygen, but really you're getting more and more hypoxic, and next thing you know, you're crashing the airplane. So those masks are set up to basically mitigate that. Now, most of the passenger masks aren't that way. They're not. The passengers can kind of pass out. You don't want that for a lot of different reasons, but like if they pass out, okay, whatever. The pilot, however, absolutely cannot pass out, because he's the one that has to operate the aircraft, talk to air traffic control, and all that good stuff. So those masks for the pilot, the co-pilot, very, very important, and any other essential flight crew that may be up there. Now, if there's a continuous flow oxygen system, there's also a demand flow oxygen system. Now, continuous flow is pretty obvious. You have a steady stream of oxygen that you will take a regulator and you will try to turn it down to the lowest level oxygen possible that you need, so that way you can conserve it, because no matter what, it's coming at you whether you need it or not, so you don't want to waste any of it. A demand flow, on the other hand, is different. Demand flow only sends oxygen whenever you inhale, so effectively it opens up a little valve, lets that oxygen come in, and then once you stop breathing, it stops flowing, so it makes it a lot more efficient. And you can listen, if you listen to, like, before, say you go watch Air Force videos, these guys flying around dogfighting it at a certain say 20, 30,000 feet, you'll hear their individual breaths, and that's because they're using a demand flow oxygen system to try to conserve that oxygen as long as possible. As they breathe in, it opens the valve and comes into their mouth, and they stop breathing, it stops flowing it, or Okay, in terms of chemical oxygen generators that you'll probably come across, the PSU is one of those, the passenger service unit. This is what's in the overhead, bins on an airliner. So whenever the masts deploy, this is what is actually supplying it. And you can kind of see the masts that have been packed right there in the middle. Now, I'll tell you, mass drop test or something that you have to do, especially on a 777, it's not a fun night, because you'll drop all those masks to make sure that they all come down correctly, fix any problems they have, but then you have to repack all those masks. They have to be repacked in a very specific way, and they have to go up into those PSUs, and then the PSUs have to close. It takes a long time. There's usually like a 5 or 6 person job on a large aircraft because there's just you have to roll them up super tight and it has to be just right or else it won't work. But this will give the passengers about 15 minutes worth of breathing air. And the idea, if you have a decompression or some sort of issue like that, they're going to very quickly try to get below 12,000 feet so that way oxygen is not necessarily a problem anymore, and get on the ground as soon as possible. So they don't need a long time. Now up front with the aviators, you very well could have a canister of continuous breathing air, so that way they can get the aircraft on the ground. They're not limited to that 15-minute window. But types of maintenance that you'll end up doing is basically mask drop tests, and then you'll repack those masks and put them up in there. Now, pilot's mask inspection is another type of oxygen system servicing that you'll have to do. Every so often, these masks have to be taken out, cleaned, repacked, and then put back in there. Just part of like your regularly scheduled maintenance on anything else. What you'll do is you'll put on a pair of gloves, like white oxygen gloves. You'll unroll the things that attach it to your head, the headbands, and you'll wipe out the interior of that mask, repack it per the AMM, put it back in there, sign it off. And what that's doing is that is allowing you a chance to get to see and inspect and make sure that there's no holes or damage to the hoses, to the seal, or anything, and making sure that it's also still clean. Because the idea behind these types of masks is that there's a fire in the cockpit or there's some kind of issue, and you want to make sure that the smoke stays out of the eyes of that aviator so you can get the aircraft on the ground, and so that we can correct whatever issue it is. And so you're there to clean it, ensure that it's serviceable, and it's good to go. You won't have the same requirements for the passenger mask because passengers don't necessarily need to see anything for safety purposes. They just need to be able to be alive whenever they hit the ground, and so those masks simply just get repacked and put in there. And but the actual pilot, co-pilot mask, any of your flight crew mask, they're going to be dealt with a much higher degree of scrutiny because there's so much more riding on the pilot being able to see and operate. All right, so let's talk about oxygen servicing one more time. So this is kind of the process that you're gonna go through whenever you're servicing an aircraft oxygen system. You're gonna check all the hydrostatic dates on all the cylinders, make sure that they're within date. You're gonna make sure that they are above 50 psi. They have enough charge in them to get you where you need to go on that aircraft. You're going to also make sure that the ground the refill cart is grounded off, and so that way you don't have to worry about any sort of static discharge causing an oxygen fire. Keep in mind that this oxygen will explode on you, so it's something you want to be very, very conscious of. You're gonna make sure that you're clean, super, super, super clean, because oxygen and hydrocarbons do not get along. They will explode. There's all these like old stories of mass deploying, and some old lady put a bunch of like KY jelly or Carmex on her lips. You put it on there, and then all of a sudden she burns herself because there's a chemical reaction. So you don't want to have any kind of like any sort of oil, any fuel, or anything like that on your hands or on your clothes whenever you're servicing oxygen, because it's a serious hazard that you need to be conscious of. Anyways, then you're going to connect the cart from the hose and begin to fill it. You're going to watch the pressure go up, but you're also going to watch the pressure on the bottle itself, make sure that it doesn't drop below it too low. Whenever the cylinders are equalized and they're where you need the aircraft to be, then you're simply going to do everything in reverse. Make sure that you put the bottle back the way you found it. Make sure that it's super safe and taken care of, so that way you can use it again next time. Always do future you favors, so that way you're set up for success next go around.